Welcome to the deep dive. We sift through complex topics, pull out the essentials, and basically give you the inside track. Okay, let's unpack this. Imagine you're gearing up for a major med school exam, right? And someone hands you this brilliant guide, like a cheat sheet, but way more insightful for the really tricky concepts. That's kind of what we're aiming for today. We're diving deep into vaccination power in global health, tailored specifically for you, thinking like a first-year medical student. We want to go beyond just the basics, really uncover the how and why, link the different vaccine types together, and give you some solid anchors, memory aids, all drawn from reliable medical sources.
Yeah, you set that up perfectly. This is, well, it's crucial stuff because we're talking about maybe one of the single most impactful public health interventions ever. Really, this isn't just, stopping someone from getting sick. It's bigger. It's about changing the health story for whole populations, preventing millions of deaths every year. And for you, starting out in medicine, understanding vaccines is just fundamental. It connects immunology, public health strategy, and maybe most importantly, how you'll talk to your patients one day. It's core. So just to get you thinking right away, can you name a disease that's been completely wiped out, eradicated thanks to vaccines? Just keep that in the back of your mind. We'll loop back later.
Oh, that's a great one to mull over. So let's kick things off with the basics of immunity. We all have some familiarity, but let's quickly refresh because it's the foundation for understanding vaccines. First up, passive immunity. Think of it like a temporary loan of protection. Newborns, right? They haven't seen many antigens yet, so they get this short-term shield from their mother antibodies crossing the placenta, and then more through breast milk, like IgA, IgM. But here's the catch, and it's a big one. No memory cells get made. It's like borrowing that car. You can use it for a bit, but you don't learn how to build one, and you definitely don't keep it. It just fades. Which naturally brings us to active immunity. Now, this is where your own immune system learns the ropes. It builds its own defense arsenal, complete with memory B and T cells. It's how we get immune after we actually encounter a pathogen, like getting chickenpox as a kid. Your body fights it, remembers it, and is ready next time. But surely there's a better way than just getting sick, right?
that's
A
right.
safer way.
Absolutely. And that hits the nail on the head. Why choose active immunity via vaccination instead of just, letting nature take its course with the actual disease? The why is really the core of what vaccines are all about, their prophylactic nature. The whole idea is to train your immune system. Teach it to recognize and fight pathogens before they make you seriously ill. It's exposure, yes, but without the full risk. Think about training for a boxing match. Would you rather step into the ring first time against a heavyweight champion going all out? Or would you prefer sparring with a skilled trainer who knows how to push you, teach you, but crucially, keeps things controlled so you don't get badly hurt? Vaccines are that controlled trainer. They prevent infections before they happen. And that's why the WHO calls vaccination a simple, safe, and effective way of protecting you against harmful diseases before you come into contact with them.
Huh.
And the impact is just staggering. We're talking 3.5 to 5 million deaths prevented annually from things like diphtheria, tetanus, pertussis, flu, measles. The list goes on.
Okay, wow. So if we're designing these amazing training drills, what qualities do they absolutely need? What makes a vaccine not just work, but be really good in the real world for everyone? Actually, before we list them out, just take a second, you listening. What would your perfect vaccine look like? What features would it have? We actually have a neat little mnemonic to help remember the key characteristics. Think SAFE EHAOLS. Maybe you could break that down for us. What does each letter really mean in practice?
Yeah, safe HHILS is a great anchor. And achieving all of these, it's a huge scientific challenge, a real balancing act. Let's unpack it. S is for safe. Top priority, obviously. It has to protect effectively without a significant risk of causing disease or serious side effects. Non-negotiable. A is for administered easily. Think logistics. Mass vaccination campaigns need something practical. Easy administration helps reach more people. F is for few adverse effects. Minimal reactions. Sore arm is one thing, but severe systemic issues. We need to minimize those. E is for efficient. It needs to actually work well, stimulating strong immune responses, T cells, neutralizing antibodies, the whole package. H is for high immunogenicity. This is about provoking a strong and reliable immune response in pretty much everyone who gets it. A is for long-lasting immunity. We want protection that sticks around, ideally for a long time, meaning fewer shots, fewer boosters needed over a lifetime. L is for low cost, cost-effective. It has to be affordable, economically feasible for widespread use, especially globally. That's crucial for equity. The second L seems like a repeat of long-lasting, which we covered. Important, though. The first S was safe. The next S is for stable. It needs to hold up during storage, transport, use in different climates. You can't have it degrading easily. And the final S is for broad protection. Ideally, it protects against multiple strains or variants of a pathogen. That's a big plus. So you see, hitting all those marks, that's the goal, and it drives a lot of vaccine research and development.
That makes perfect sense. It's a tough checklist. So now for the really cool part. How do scientists actually make these different training drills? The technologies behind them. There are several clever strategies, right? Each like a different chapter in the instruction manual for your immune system. Maybe you can walk us through the main types, and let's keep using polio as a running example.
Mhm.
It's such a good case study for seeing these technologies in action against a disease that, well, used to cause paralysis and widespread fear. It mainly enters through the mouth, often contaminated hands, causing spinal bulbar or bulbospinal paralysis.
Perfect. Polio is ideal because its history really mirrors the evolution of vaccine tech, showing the different approaches and their trade-offs. Okay, first up, inactivated vaccines, sometimes called killed vaccines.
Right, the mugshot approach, like showing your security team a detailed photo or blueprint of the bad guy, but the bad guy is definitely not there and can't cause any trouble.
Exactly. The key word here is safety. These are made from the pathogen, but it's killed using heat or chemicals. It can't replicate, can't cause disease. Zero risk on that front. It triggers an immune response, mostly antibody-based. The Salk vaccine, the inactivated polio vaccine, or IPV, is the classic example. Given by injection, it was revolutionary, slashed polio rates dramatically. But the trade-off, because it doesn't mimic natural infection route fully, IPV gives very little mucosal immunity in the gut for polio. So someone vaccinated with IPV might not get paralyzed, but they could potentially still carry the virus in their gut and spread it. Other examples, Hep A, rabies, some flu shots.
Mm-hmm.
Okay, next, live attenuated vaccines.
Ah, the sparring partner vaccine. Instead of just a picture, you bring in a weakened opponent. Still live, can still move around a bit, simulates a real fight, but they've been significantly slowed down, disarmed. Your immune system gets a proper workout without the risk of a knockout.
Great analogy. The core idea here is strong, long-lasting immunity that closely resembles what happens after a natural infection, because the weakened virus can actually replicate a little bit in your body. It triggers a broader immune response, including cellular immunity and often mucosal immunity too. The Sabin vaccine, the oral polio vaccine, or OPV is the famous one, given on a sugar cube. Big advantages: it induces gut immunity for polio, stopping transmission, and the weakened virus can spread person to person, indirectly vaccinating others in the community. That's huge for eradication efforts. Other live attenuated vaccines include MMR measles, mumps, rubella yellow fever, BCG for TB. They often give very long immunity, sometimes lifelong, with fewer doses. The trade-offs: they need careful cold storage. And there's a very, very small risk the virus could mutate back to a more harmful form. Vaccine-derived polio is a known, though rare, issue, and they're generally not for people with severely weakened immune systems. All right, moving on to toxoid vaccines.
Okay, so some bacteria cause harm by releasing toxins, right? So this approach is like learning to defuse a bomb. You study the bomb's nasty parts, the toxins, but the actual explosive charge has been removed. So you practice neutralizing the dangerous weapons safely, not necessarily the whole bomber.
Precisely. The insight is target the weapon, the toxin, not the whole bug. Toxoid vaccines are made from the inactivated toxins produced by the bacteria, usually treated with something like aluminum salts. They train your immune system to neutralize that specific toxin. Think tetanus and diphtheria shots. They're very safe, very stable. The main limitation is they only protect against the effects of the toxin. They don't stop the bacteria from colonizing you, necessarily. And immunity can wane, so you often need boosters. Then we have subunit vaccines.
Right, so maybe you don't need the whole mugshot or the sparring partner. What if just recognizing a specific piece of the enemy's uniform, like a distinctive patch or insignia, is enough? Using just a fraction, a subunit of the pathogen.
You got it. The core idea is precision plus safety. You identify a key protein or piece of the pathogen, the subunit that the immune system can recognize. You produce just that piece, often using recombinant DNA tech. Since it's only a small part, there's zero chance of causing infection. The Hepatitis B vaccine is a great example. It uses just the virus's surface protein. A cellular pertussis is another, uses purified components of the bacteria. They're generally very safe, stable, few side effects. The potential downside: sometimes these isolated subunits aren't as immunogenic. They don't provoke as strong a response on their own. So they often need...
They need those alarm bells we mentioned earlier, the adjuvants.
Exactly. They often need adjuvants to boost the signal. And producing just the right subunit can sometimes be complex or costly. And building on that idea, we get conjugate vaccines.
Okay, so sticking with the uniform patch idea, sometimes that patch alone isn't very attention-grabbing, especially for, say, a rookie immune system, like in infants. So you cleverly sew that subtle patch onto something really bright and flashy, something the immune system definitely notices, makes the important patch stand out.
Perfect metaphor. That's exactly the insight for conjugate vaccines. Enhance the response to tricky antigens, particularly polysaccharides, which often don't trigger strong T-cell dependent memory in young kids. You take that poorly immunogenic polysaccharide patch from the bacteria and chemically link it, conjugate it, to a more robust protein carrier like a toxoid flashy uniform. This combined molecule gets processed differently by the immune system, leading to a much stronger T-cell dependent, long-lasting response even in infants. The Haemophilus influenza type B, or Hib, vaccine is the classic success story here, dramatically reduced hive meningitis.
Okay, a couple more modern approaches. Viral vector vaccines. Oh yeah, the Trojan horses strategy. This one's smart. You use a harmless virus, the vector, as a delivery vehicle. You sneak the genetic instructions for just one specific protein from the real bad guy pathogen inside this harmless virus. The harmless virus then delivers those instructions into your cells, and your cells become little factories, churning out just that one enemy protein. The immune system sees it and learns to recognize the enemy without ever meeting the actual dangerous pathogen.
That's it. The key advantage here is the ability to induce a really strong cellular immune response, meaning T-cell responses, which are crucial for fighting intracellular pathogens like viruses. So a gene from the target pathogen gets spliced into a harmless vector virus like an adenovirus. That vector infects cells, delivers the gene, your cells make the protein, and you get potent T-cell memory. Examples include the Ebola vaccine and some of the COVID-19 vaccines like AstraZeneca or Johnson & Johnson. They can offer strong, broad immunity and often faster development. Potential challenges. If you already have immunity to the vector virus from a previous infection, it might dampen the vaccine's effectiveness. And very rarely, some side effects like blood clotting issues have been associated with certain adenoviral vectors. And that brings us to the newest kid on the block, mRNA vaccines.
Right, the cutting edge stuff. Instead of delivering a virus or even a protein, you're delivering just the instructions, the mRNA blueprint, straight to your cells. It's like FedExing your cells the recipe for making one specific part of the pathogen, like the SARS-CoV-2 spike protein. Your cells read the recipe, bake that protein, display it, and your immune system learns to attack it, all without seeing any actual virus particles. It feels quite futuristic.
It is pretty revolutionary technology. The core insights are speed, flexibility, and safety. The mRNA tells your cells what protein to make, your body makes it, mounts an immune response, and then the mRNA itself degrades very quickly. There's no virus involved, no risk of infection from the vaccine. The Pfizer BioNTech and Moderna COVID-19 vaccines are the prime examples. Big advantages are how fast they can be developed and potentially adapted to new variants. They trigger strong antibody and T-cell responses. The main considerations initially were the need for ultra-cold storage due to mRNA's fragility, and because they're newer, we're still gathering very long-term data, although the safety profile so far looks excellent based on billions of doses.
Wow, that's quite the toolkit of strategies. So we have these incredible training manuals. But you mentioned earlier, sometimes they need a bit of help, a nudge for the immune system. The support crew. Let's talk about adjuvants again. You called them alarm bells or flares. They shout, hey, immune system, pay attention. This thing here is important. How do they actually work that magic?
Yeah, that's a good way to think about it. Adjuvants are basically immune stimulants added to vaccines, particularly subunit or inactivated ones, to boost a response. They work in a few ways. They can create a little depot effect, holding the antigen at the injection site longer. They can activate innate immune cells, providing that danger signal that says respond strongly. They help attract more immune cells to the area, enhancing antigen presentation, leading to a more robust and durable adaptive response, more antibodies, better T-cell activation. Aluminium salts, like aluminum hydroxide or phosphate, are the most widely used adjuvants. Been used safely for decades in vaccines like DTaP, Hep B, HPV. Some newer vaccines use other things, like the HPV Cervarix vaccine uses MPL, which is a modified, less toxic version of LPS from bacteria, a very potent immune stimulator. And besides the antigen and adjuvant, vaccines have other bits too, right? Suspending fluid, usually sterile water or saline, and sometimes tiny amounts of preservatives like thimerosal, though largely removed from childhood vaccines in many places, stabilizers or antibiotics like neomycin, to prevent contamination and keep the vaccine stable. And yeah, how you give the vaccine matters too. Most are injections, deep subcutaneous or intramuscular. That's standard. But oral delivery, like the Sabin OPV, is brilliant for mass campaigns, especially in kids. Intradermal, just under the skin, like the BCG for TB. Scarification, scratching the skin, was used for smallpox. And even intranasal sprays for some live attenuated flu vaccines, aiming for mucosal immunity in the airways. The route is chosen for effectiveness and practicality.
Okay, that makes sense. Delivery method matters. Now, remember that question from the start. How do we protect people who can't get vaccinated? This is where that concept of herd immunity comes in, right? The community shield.
Exactly. Herd immunity or community immunity is fundamental public health. It's the indirect protection that happens when a large enough proportion of a population is immune to an infection, whether through vaccination or prior illness. When that happens, the chains of transmission get broken. The pathogen can't find enough susceptible hosts to keep spreading effectively. And this protects everyone, but especially the most vulnerable who might not be able to get vaccinated themselves. Think newborns too young for certain shots, people on chemotherapy, those with primary immunodeficiencies, or severe allergies to vaccine components. They rely on the herd around them being immune.
So it's not necessarily that everyone has to be immune, but enough people do to stop the spread.
Precisely. And that enough, the threshold varies, depending on how contagious the disease is. For something like polio, you need maybe 80–86% of the population immune. Diphtheria, around 85%. But for a super contagious virus like measles, you need really high coverage, like 95%, to maintain that protective bubble. And this brings us back to that polio story, the recent news from London. Finding vaccine-derived poliovirus in sewage samples. What does that tell us? It highlights that even the weakened oral vaccine strain, if it gets into an under-vaccinated community, can circulate, potentially mutate, and pose a risk again. It's a stark reminder that we absolutely must maintain high vaccination coverage to keep that community shield strong. Complacency is dangerous.
That's a really powerful point. Okay, so no medical intervention is totally risk-free, vaccines included. For us as future clinicians, it's crucial to understand potential adverse effects and also who shouldn't get certain vaccines, the contraindications. You hear terms like adverse event and adverse reaction. What's the difference? It seems important.
It's a critical distinction. An adverse event following immunization, AEFI, is any negative health occurrence that happens after someone gets a vaccine. It might be related, or it might be pure coincidence. Someone could get a vaccine and happen to catch a cold the next day that's an adverse event, but not necessarily caused by the vaccine. An adverse reaction, on the other hand, is an adverse event where there's evidence suggesting it was caused by the vaccine itself. It's a noxious, unintended response linked causally. Understanding this helps with accurate reporting, investigating safety signals, and importantly, communicating clearly with patients. Most vaccine reactions are mild and expected.
Like a sore arm, maybe a bit of fever.
Yeah, exactly. Local reactions like soreness, redness, swelling at the injection site are common. Systemic reactions like mild fever, headache, muscle aches can happen too, usually short-lived. These just show the immune system is kicking into gear. Serious adverse reactions are very rare, but they're monitored closely. Now, contraindications who shouldn't get a particular vaccine, generally anyone with a history of a severe allergic reaction, like anaphylaxis, to a previous dose of that vaccine or one of its components. That's usually an absolute contraindication. Also, people who are acutely ill with a high fever might have vaccination postponed. Certain immunocompromising conditions are contraindications for live attenuated vaccines, think severe combined immunodeficiency, SCID, or significantly weakened immunity from HIV or high-dose steroids or chemo. Specific neurological conditions might be relevant for certain vaccines too, and a recent blood product administration can sometimes interfere with live vaccine response. It's about careful individual assessment.
Right. Personalized medicine, even in vaccination. Okay, so wrapping this up, what's the big takeaway for a medical student listening to this? We've covered the immune system's training manuals, the adjuvants, the community shield. Ooh. And that question from the start, the disease totally eradicated by vaccination.
Smallpox, a truly monumental victory for global health, achieved through a coordinated worldwide vaccination campaign using a live vaccine.
Yeah.
It proves what's possible. It really is. And it's not just history. That victory and the principles we've discussed today are still shaping how we tackle infectious diseases. So maybe the final thought for you as you continue your medical journey is this. We live in a world with emerging pathogens, evolving challenges, and sometimes significant vaccine hesitancy. How will your deep understanding of how vaccines work, their benefits, their limitations, empower you? How will you use this knowledge not just to treat patients, but to be an effective advocate for public health, to communicate confidently, and to help maintain that vital community protection? Because using vaccines effectively, alongside strong public health measures, remains our best defense against so many devastating infections. It's an ongoing effort every single day.
That's a powerful challenge and a perfect place to end. Thank you for joining us on this deep dive. Keep exploring these topics, keep asking questions, and always remember the incredible power of prevention. Until next time, keep digging deeper.